Alright team, so as I told in learning how to approach sessions, the idea is going over the problem from the beginning. Like normally we do a problem that we have never seen before, but for the sake of giving you an experience on a problem that is on a relevant topic, we have chosen a value from the previous progress sheet. I think it's also in yours. So technically I have seen this problem. Normally we do it in a way that it should have been a problem that I've never seen, but it's been more than a year, so I don't remember the problem. And what we are going to do is, we are going to solve the problem from the beginning. Like we will first see how we understand the problem, what kind of key points we care about, and then we will think about it to come up with a working solution. And we are going to feel comfortable with our working solution on the paper or on the whiteboard. And then we are going to jump into coding. And obviously before getting there, we will do some checks. We will think of what is going to be the time complexity, are we using any extra memory, and so on. So once we are clear, we have confidence in our logic, and then we are going to go ahead and do the implementation. And while we are doing the implementation, I will continue explaining what I'm doing or what I'm trying to do. And then by the end, we are going to test it with some good cases and hopefully get it past all the tests on lead code. So this is how the session is going to be. And if any questions rises, please feel free to raise your hand and ask, because that way the session is going to be more useful. So obviously it's going to take longer than how I would solve this problem in an interview, because I will be explaining each of these steps. So the idea is to show you how indeed we are approaching to the problem at different stages. Like when we first face with it, when we get the information, when we build our solution and go ahead with the implementation. So at high level, does that make sense? All right, in that case, let's get started. Welcome to the first learning how to approach session for the second group. So our problem is from lead code, and it is named longest Univalue path. Given the root of a binary tree, return the length of the longest path where each node in the path has the same value. This path may or may not pass through the root. Okay, so we are given the root of the binary tree, and we are looking to find the longest path in the tree. I guess a path starts from one node and goes to another node, and they have to be connected all through edges. And all the nodes that we are visiting on this path are supposed to have the same value. So we are given the root to have access to the tree. At the same time, this path, this longest path, doesn't have to start from the root. So there is no guarantee that the value we are going to be looking for is going to be root's value, right? If it's not passing from the root, it is possible that it can have different value than root's value. Like the nodes that are going to be in the longest path will have a different value than the one in the root. All right, and I think we are supposed to return, let's see, an integer which represents the length of the path. And the length of the path between two nodes is represented by the number of edges between them. Meaning, in the first example, the longest Univalue path obviously starts from the root and goes to the right. So we have three nodes, but by the definition of the question, it says the length of the path is number of edges. Meaning, the path length we should report for this one must be 2. So, up to this point, what did we do? Like first off, this was a very easy question to understand, very short description. But there are a few points which are key, which if we miss, we can go into wrong directions. So the first one is, the root may or may not be part of the longest path, right? Meaning, in our solution, we should somehow consider other values as well. It doesn't have to only touch, it doesn't have to touch to the root. And also the second one was, if you ask me without giving me the definition of the length of the path, I would return 3 for this example, rather than 2. And since they define it by the number of edges, but not the number of nodes, the desired answer is 2. So this is another thing that I would say I would be careful in my implementation. All right, so I think the first example is pretty clear, right? And let's take a look at the second example. Well, yes, so the second example indeed here reveals a situation that wasn't extremely intuitive to me at the beginning. Like now, we see that a path indeed can have like two subpaths, you know, one coming from a left subtree and the other one coming from a right subtree of a node. Like here, we see this in this example, right? Normally, I could have considered only going like this, you know, instead of thinking that, oh, it may start in one, you know, in the lower levels and then end in the lower levels. So it can pass through the other nodes. So this example indeed made it clear to me that we should consider this situation as well. All right, and lastly, we have the constraints. So in some of the interviews, you may be provided constraints. In some other interviews, the interviewer may hide this information on purpose, or they may not provide this just to see how well you're going to perform. Because if you know the constraints tell you a lot about the question. So now that we see the number of nodes is not going to exceed 1,000, what does this tell us about this question? Do I have to force for a linear solution? Linear meaning ON. Do I have to force for a linear solution for this problem? We don't really have to, right? Because 1,000 is small enough that n log n would work perfectly. Even n squared, like we are just doing 1 million calculation, if we don't have huge constants, n squared should do the job for this problem as well. So when you look at the constraints can give you a hint on what kind of asymptotic complexity is desired in the efficient solution or in an acceptable solution. Does that make sense? But at the same time, we shouldn't build so much of a dependency on the constraints. Because in some interviews, the interviewer on purpose may hide this information. Because they may want to see how much you wanna take it. You know, sometimes maybe this question also has ON solution. Like even if the constraints are not pushing us for that, we may be able to find an ON solution. We don't know. We are going to jump into that part soon. But in general, we shouldn't forget that if the constraints are available, they tell us a lot about what kind of asymptotic complexity is desired in an efficient solution. So it's not just about number of nodes, right? Also the values are also important, right? Because we are checking the longest path with the help of values, right? So the range of the values would matter too. And here we also see that the range of the values are between -1,000 and 1,000. And there is a guarantee that the depth of the tree will not exceed 1,000. And indeed, guys, I have read the constraints in a wrong way. So I told you that there are 1,000 nodes. But indeed, there are 10,000 nodes. So again, like this is a very good lesson, right? If we read it wrong, we can get the wrong impression about the question. So that's why, like, for all the given information, we should process it very carefully. And don't make like misreads, try not to make misreads and miscalculations. So how can we avoid this? We can take a second look. We can take a third look, right? How much is it gonna take to reread the description of this problem? Maybe 1 more minute? That's it. And if it's gonna give me a guarantee that my understanding is good about the question, I would definitely give that minute. Because if I read the constraints wrong and develop a confident n-square solution, and by the end, if it turns out that they were looking for n log n solution, this wouldn't be nice, right? So we better spend a little more time to get confirmation on our understanding about the problem so that we are not going to solve the wrong problem. Because the first step of solving a problem is understanding the problem. Cool. So, about our understanding right now. Is everybody clear what the question is asking? Okay, cool. So now, let's think of what kind of solution we can build. So here, the first solution that comes to my mind would be checking different values. Since the value range is small, like checking different values, starting from -1,000 to 1,000, one by one, and see what is going to be the longest path for a given value. So how can we do that? Let's think about that. Let's say I started from the root, and let's say the first value I'm going to check is 5. So since the root's value is 5, I can continue expanding from root, right? And which directions can I expand at the root? I can either go left or to the right, right? This is the case for any kind of node in a binary search tree. So at 5, I can ask my left child, hey, give me the longest path length with value 5. And I can ask my right child too, hey, give me the longest longest path that passes through you, but that takes only one side of you. Because if we want to get it, like imagine, we want to avoid the case where like we have 5 here, 5 here, 5 here, 5 here. So if you ask this guy directly, okay, so what is the longest path that you are inside? What is this guy is going to return? It's going to return 3. Because once you think about it, this is the longest path it's in, right? Length. So right now, let's say we are returning the length of the path. So right now, if I ask this node directly, hey, what is the longest path that you can generate with univalues? The answer is 2, right? Like the path description of the question, number of edges. But here, indeed, I cannot add this one on top of this. Does that make sense? So if I am asking to my child about its value, like if I'm considering getting its value and putting it on top of mine, then it has to make sure that it's not taking into account both sides. Like it can get one of the children, but not both. Does that make sense? Okay. So if we go with this approach and ask our children, okay, we started from the root, and then we asked our children if it has the same value, then we say, okay, so give us the best. We actually we are asking 2 types of information here from our children. We may either return the best result that is found from here, because it can be the answer, or like imagine a tree like this. What would be the answer here? 4, right? So if we just simply ignore 1, 2, 3, no, it's going to be 4. 1, 2, 3, 4. So you basically count the number of edges, right? So like this is one possible path, this is a second possible path, and this is the third possible path. Does it make sense? Okay, so now let's imagine like what is going to be the most naive solution with 100% accuracy. So what we can do is we can start from each node and try to expand as much as possible, right? What do we mean by that? Let's say we started from root. Root can say, okay, so get the best solution from right, get the best solution from left. If you can merge, try to merge and report the best result to your parent. So if we do it this way, we can solve what is going to be the, let's say, if we are at this node and we say that we are going to report the best result, this can return 4 with this logic, right? But if we return 4 and if we get the best result, including left and right side, we may not be able to get a longer path in case of like using this. Because now like this 4 is not able to be merged with this path, sorry, this edge. But these 2 results, indeed, they could have been merged, right? So we should separate. We should kind of we should report back this information somehow to the previous node, so that we can make use of it. So what ways do we have at the moment? We can either report 2 information at the same time. So instead of returning only an integer, we can have an helper function, and that helper function can indeed return us a pair. Like one can tell what is the global result, and the other one can tell what is the maximum you can get if you choose one direction, either from left or right. Because the solution that comes from either left or right can be merged with us. But the global solution, if it is using both ends, it's not going to be using, like it cannot be merged with this one. Okay, so now let's think a little more, because now it's not extremely clean. Like we are trying to report 2 things, which is still doable, but let's think a little more if we can even make our solution simpler. Like one thing that I noticed is we don't have to deal with all the different values, you know. Indeed, we can start these operations from the nodes. Like if the root's value is 5, we know that root can only appear and contribute to the solutions of paths which is consisting of 5, right? Like we are not able to change the values. So whatever value you have in your node, that value will be the one that you are going to use to generate the longest univalue path, including yourself. So right now I am kind of like cooled off the idea of using different values and trying them what is the longest path with this value. Right now, instead of that, doing the operation with the help of nodes can make more sense. So I'm yielding towards that idea. So how can we do that? Like currently we are entering our journey from the root. So what can we ask to our children? Indeed, we can ask them to report us two things. So right now, I'm also okay with reporting two things because these two information is going to be very useful. One is the global solution, and the second is what if we have to choose one leg? Because the global solution can come from merge of it, right? But the one leg solution can be added to our solution, and we can generate even a bigger one. So I think I'm gonna go with the way of reporting these two information, and I'm gonna implement a recursive code. So I'm gonna ask my children to calculate this out, and then report me back what is the longest global solution they are part of, plus, or for the global solution we may even say they don't have to be part of. It can keep track of the global solution. Like with implementation, it's gonna be more clear. But for the other one, we should ask for, okay, so what is the single path that you can generate with your value? And if our values match, we will also consider adding the coming solution from our children on top of what we find. Okay, so right now with this solution, we are not going to be visiting the same node twice. Let me think. Yes, we are not going to be visiting the same node twice. And are we going to be using any additional memory? We are going to be using the call stack. We may have to keep these states in our call stack, obviously. And since the depth of the tree is limited with 1000, which is less than n, it looks like we are going to be using only linear amount of memory. Like 1000 is less than 10,000, but since it's close to the order of n, I would say the additional memory we are going to be using is going to be ON as well, since 1000 is close to 10,000. Okay, so like I will say now I have a clean working solution in mind, and I am convinced that it's going to be working. And let's see how this is going to play out in execution. Because like now I'm an experienced programmer, right? So if I start with this confidence level, it might be enough to get it done. But in an interview setting, let's say if you want to get more, let's say, confidence in your solution, you may trace it on the examples. So now let's give it a try with the given examples. And hopefully this is going to make the algorithm more clear in your minds as well. So the first example we have is 5, 5, 5, and 4, 1, 1. So we start with 5. And then 5 makes two calls to its children, to the left one and to the right one. To the left one, it asks two things. So for all of them, we are asking two things. One is the best global solution that we have formed in this subtree so far. And the other one is, what is the single leg solution? It's either you are allowed to get your left or you are allowed to get your right. And you can add yourself on top of that too. So, let's see. 5 made the call to 4. 4 made the call to 1. Does 1 have any children? No. Since we are at the end, we know that the best global solution we find has actually 0 edges. And the legs that we can generate also has 0 edges. Right? Therefore, 0, 0 will be reported back to 4. And then 4 is going to make a call to right children. And this is going to report back 0, 0, 2. And at this point, 4 will look when it gets result from 1. Can it add this result on top of 4's global result? No. Therefore, we don't even consider making use of this value and add something on top with us. And let's look at the right leg. Is this value equal to our value? Again, we cannot make use of this, right? Therefore, like the second parameter we are going to return, so the second one represents, let's write it here. Second value represents best single direction solution. It can be merged if caller has the same value. Second. Okay, value is okay, I guess. First value represents best global solution that is found in the given subtree so far. By the way, what do I mean by subtree? I think the definition must be very intuitive. So here the subtree is this guy. Like the subtree that starts from this node is this guy. Does that make sense? And the subtree here is this one. And the subtree here is equal to the full tree itself, which is this one. Okay, so now let's continue. Now that we didn't have equal value with our children, we know that we couldn't get any result from them. And the longest result we can get from one direction choosing is 0. So the global result, the best global result that we have found so far, it is also 0, right? Because we couldn't find any matches so far. So now we are going to go to the other direction. So after these results come in, so in order to decide on this value, we have to calculate both of them. Because maybe one of them is going to be helping us. That's why I'm not writing anything here. But from the left side, the result that is coming is 0. So now we are looking at the right side. And on the right side, we make a call to this guy. And this is not a leaf, so it's going to make this call. It doesn't have a left child. And here, 5 is a leaf node. And we know that for the leaf nodes, the result is going to be 0, 0. And then when we make a call back, we return back to here. Now we check. From the left, did we get any results? No. From the right, what did we get? 0, 0. But do we have the same value? Yes. So, therefore, we can indeed add ourselves on top of the result that is found in this subtree. That's why now our single leg solution will be increased by 1. From 0, it's going to be 1. Because the best result that came from my right subtree was 0. And I added myself on top of that. And it is one direction, right? It's not like I'm adding both directions. So that's why this is going to be 1. And now let's take a look at the global solution. What is the best global solution I found so far? It is also 1, right? So this is how this is going to look like. And once this reports back to the root, now the root first checks. What is the single solution I can possibly get? And here it sees 0 and different values, so it can be 0 from left side. And from right side, there is 1, plus there is a value equality, meaning I can add myself on top of what I found on the right subtree. So this value is going to be 2 here, therefore. And how about the global solution? So the best global solution I found so far was 1, and now I found the solution with 2. So what is going to be new global solution here? 2. Does that make sense? Okay, so now let's also quickly see how this is going to play out with the second example. So here, the reason I want to process this example is to show you that we should be careful with updating results when it comes to merging results from 2 subtrees where their values are equal to ours. Because in this case, we should also consider the fact that we can add results on top of each other. That is coming from our left children and that is coming from our right children. Once we also cover this example, I think we will be ready to jump into coding. Alright, so let me use this area for this example. And this time we have 1 in the root. Or let's just use the numbers, the circles. So 1, 4, 5. Then we have 4, 4, and 1 more 5. Okay, so 1 is going to make the call to here. And then 4 is going to make the call to here. And we know that these guys are 0, 0 everywhere. And here. So 0 came from the left. And I have an equal value here, right? So there is a possibility of putting 1 from here. And 0 came from here and I have the equal value. There is a possibility of putting 1 from here. So what am I going to put to the left? Sorry, to the second field. Louder. 1. Yes. The reason is I have an equal value, therefore I can add myself to the best result that is found. In either way, the best result was 0. When I add myself on top of it, it's going to be 1. Since I'm equal with both of the values, that's why I can consider adding myself on top of both. So now let's take a look at the global result. So when we are updating the global result, there is one exception that we shouldn't forget about. If both our left and right children have equal value to my value, what I can do is, I can get both results, like their best results, and then add 2 on top of them. Why is it 2? Because we are counting number of edges we have in the path, right? And this subtree has this many, let's say n edges. And let's say this subtree has m edges. In total, if I create a solution with these, and these 2, the number that I'm going to write here is going to be n plus m plus 2. Does that make sense? So if the longest path that I found here was n, all the edges, they will be counted here too because they are part of force path, right? Again, guys, this is important. We are not getting the result from the global field. Like once we do the implementation, it's going to be more clear. Because the global result may come from different values too. There is no guarantee. Or it may be using 2 different legs. Let's say there were 2 more fours here. The global result here for this sub-problem is going to be 2, right? Actually, do you guys want to consider that case? I think it's going to look nice and it's going to make things more clear for us. So let's remove this, and we have 4 here, and let's say we have 2 more 4s here. So we know that this result is going to be 0, 0, this one is 0, 0. Okay, so now let's do the consideration for here. What is going to be my left result? We have already seen it from the previous example, it's going to be 1, right? Because it's 0 here, but since they both have equal values, I can add myself to any of them. And if I have to choose single direction, I cannot choose both. As a result, this field is going to be 1. And once we look at the best global solution, here, this 4 considers the exceptional case as well, which is, oh, if we are equal to our left and right, indeed we can get both of their single paths and add 2 on top of that. And that's why the global best result we have found here will be 2. Does that make sense? Okay, so now when we do the switch from here to here, so for the single direction, if I put it over the right child, the result is going to be 1. If I put it over the left child, what is going to be the result? 2. Therefore, I'm going to be choosing the left one because it gives me a better result. And now this part is the part where we should be careful. So here, if we directly try to add ourselves on top of the global solution, we are going to make a mistake. The reason is, this global solution has already used the idea of merging 2 legs, right? And if I do merge 2 legs again, I'm going to create something that is not a path. Does that make sense? So that's why at this stage we got to be careful. And if we are merging a solution, we can only get the updates from our single directions. So here are single directions 1 and 0. And I consider using both of them and adding 2 edges. So this way I can indeed generate a solution for 3. Does that make sense? So I get the 2, like this one says 1, right? So, sorry, here, like this one says the single leg solution is 1. This one says the single leg solution is 0. So I get both results. As a result, I have 1 edge. And I added 2 more edges. The edges that are connecting me with these 2 subtrees. And that is going to be the total solution. And is this solution better than what I found so far? So we had the value of 3, right? And it is better than 2. Therefore, we updated this with 3. And here, when this is doing the updates for this guy, so let's do the right part too. And this is going to say the global solution I found is 1, and the best single leg solution I found is 1. So since 1 is different than 4 and 5, the best single leg solution that 1 found is 0. And since it's not going to be able to add it to any of the children's solutions, what we are going to do is we are going to compare these 2 global best results. And since the left one's result is better than the right one's result, we are going to get that one. And as a result, 3, 0 is going to be the final output that we will return from our helper function. And then first, of the returned result from the helper function will be returned by our original function. So is the question, is our approach clear at the moment? And now are you guys able to see why like this example is indeed covering the edge case that we want to be careful with? Because there can already be a solution in our subtrees where we have already used our joker of merging two paths, two single paths. And if we do it before, we are not going to be able to do it later. To be able to keep track of that, that's why we are returning two fields and keep track of the single leg results too. So are we all clear with the solution? And feeling good about jumping into implementation? All right, let's do that. Okay, cool. So, like now that we have already clarified pretty much everything about our algorithm, you're going to see that the implementation is not going to be a bad experience. So, we have already realized that we want to return two things. And in this function signature, as you see, it's just returning one integer, right? So I'm going to be defining a helper function. So we will be returning, so this is C++, and let's say we can use a pair. So it's been a while that I didn't implement it in C++, so let's take a quick look on a pair example, just to remember the syntax. So we define a pair, and is it under utility? Yes, so we need to add, but probably it's already included in lead code, so we don't have to deal with the header. And then we define the pair this way. And okay, let's get this example just for the sake of business. All right, and what are we going to return? We are going to return the first value coming from our helper function. Longest univalue path helper root. Do we have to pass any other variable? I don't think so. I think everything else is going to be coming from the children. That's first. And now we are going to, we are approaching top-down. So I think everybody is clear why we are using a helper function, right? Because we need to return two things, and in the given function signature, that is not the case. And we are going to be returning an integer pair. And the function name is longest univalue path helper. And it's going to get a tree node inside. And this time I'm not going to name it as a root, because this function is going to be called recursively, right? And in the first call it's going to be called with the root. But in the future calls it's going to be called with other nodes in the tree. Therefore I'm going to name my variable as node. So variable naming is something that people care, because if you name your variables in a good way, you're going to make your code a lot more readable to other engineers. And when you are working for a big organization, the piece of code that you read can be written 5 years ago by a person that has left the company 4 years ago. So in order to get things done with such high number of people in such longer time span, people are very careful, engineers are very careful with their naming, their code structure and so on. So that's why those are things that they want to see in the interviews as well. So you may think that this is not a big deal, right? It's just a variable, but they may get some reads from the way you name your variables. And like anything else, the earlier you start practicing it, the better you get in time. So I highly recommend putting some time thinking into naming your variables. Like read some good practices in your favorite programming language. This is going to be helpful in the long run, not just for interviews, but to write clean and concise codes. Cool. So now we started. If the node doesn't have any child, right, that's one case. If not node left and not node right, then it means we are a leaf. And what was the result when we are a leaf? It was 0, 0, right? So right now I'm just going to test my code, because, and I highly recommend this in your development too. Like if you are in a computer where you have compiler, I highly recommend debugging your small blocks. Because there can be a problem there, right? And it would be nice to surface it sooner rather than later. Because as code grows, there is a higher risk of having bugs in different places, and debugging is going to be harder. So when you are done with one block, just go ahead and immediately test it. So now I just want to make sure I am cool with this make pair function and defining the helper function and so on. So that's why I'm going to run my code. What? Thank you. Somebody is not practicing regularly, I guess. Cool. Now let's give it a try. Okay, output is 0, which is nice. It means it is working. Like the objective was not to get the correct answer, right? And now we are able to define our helper function, and things seem to be working. Okay, so if that is not the case, if we come to this line, like if there is a return in an if condition, the bottom part is as if everything is in else, right? So everybody is able to see that this, like writing code here, wouldn't make any difference than writing code here, right? Because like if it satisfies the condition of the if, it's gonna return. So it's not gonna continue execution. And if it continues execution, it means we are in else. So there is no need to write this else. Is everybody clear with this part? So it's just a simple thing, but again, like short code is easier to maintain. And if you have your principles in writing code, like if you internalize this early on, then your codes are gonna be easier to read in the long run. So we are here and we know that either left or right exists. We don't know whether they both exist or not. There is no guarantee on that, but we know at least one of them exists. So let's see. If not left, what are we gonna do? So we are gonna get the result from our left child, obviously. Let's say pair left results. Oh, let's use the others. Left result is equal to make pair 0, 0. And I'll also have the right result field. And it's going to be a pair of 0, 0 again. So if the left child exists, then what I'm going to do is I'm going to update my left result with longest univalue hat helper, not left. And the red result is going to come from this. And then I'm going to check the existence of my right child. By the way, you may not be very familiar with C++ syntax, but I guess it's readable, right? So if you don't understand anything, please feel free to ask a question. And it's going to be very similar here. Our right result will come from our helper as well. Univalue helper, helper, node, right. So the beauty of recursion is you have to define your base case first, right? It's very important because you have to tell your recursion when it is going to stop. And right now we kind of made it, right? When we hit to the leaf node, there is no more branching. And it's going to return something for sure. So our base case is clear here. And after that, we should also define how the updates are going to take place when we are calculating the result for the problem we have in hand. So, when I come to line 31 or line 32, I know that if I have a left child, the call is already made and the result is stored in left result. And if I have a right child, the call is already made and the result is stored in right result. And right now, indeed, I'm going to be able to treat both left and right result as if both nodes exist because I initialize them with 0 value, right? And since I am looking to maximize number of edges that I include in my solution, 0 result is not going to affect anything. So if a node doesn't exist, thinking of it as, hey, it returned me the 0 result, would make things work. Does that make sense? Okay. So now let's also see. Let's also define two Boolean variables. Is it bool or is it bool in C++ bool? Left compatible, false, and right compatible. What does that mean? So basically, with the help of these two Boolean variables, I'm trying to keep track of whether the left child is compatible with me, that we have the same values, that we can be added to each other. And likewise, the right compatible is going to keep track of the same thing for the right child. Like if I try to implement this logic without variables, I can still do that. But it's going to be complicated. And defining new variables, as long as you don't, you don't allocate memory in an extravaganza manner, it's going to be okay. And here we are just getting one Boolean, right? It's pretty cheap. And you will see that it's going to make the code very easy to read. That's why we are defining them. And in your solutions, feel free to make use of this, guys. Just to make things a little bit more easier to think about, or to more clean, you can define some extra variables. And now let's see how they are going to be initialized. So at the beginning, I assume there is no compatibility. So in order to be compatible, that node has to exist, and its value has to be equal to mine. So here I will say left compatible is equal to node value is equal to node left value. So if they are equal, then the variable is going to be changed to true. If they are not equal, it's going to stay false. Does that make sense? So the reason I didn't do this assignment on top of here is, in this line there is no guarantee that left child exists. So I have to deal with whether they exist or not. In order not to deal with them, I leave the real initialization here. But the default value is false, because if I exist and my left child does not exist, then there is no left compatibility. Does that make sense? Cool. So now let's do the same thing for the right result. And right compatibility. And we're going to have here right compatible is equal to node value. If it is equal to node right value, then it means we are compatible. If not, we are not. What's that? Oh, here. Thank you very much. This one, right? Thank you. Okay. So, team, when we come to this point, when we are at line 36, so I know whether I can merge my result with my left child with the help of left compatible. I know if I can merge my result with the right child with the help of right compatible. And I already have the results. So are we ready to finish this? Or are we missing any information? What do you guys think?
Just one question.
Yes.
I think in line 22, we are trying to reach the node left and node right. What if we don't have nodes? What if node itself is null?
What if node does not exist? Okay, that's a good question. So in an interview environment, you should definitely check that. So now let's go back to the question description to see whether it is possible to have a case where we will make our first call with an empty node here. So it can be 0. Thank you very much. That's a very good catch. So it's either we can handle it here, like if node is null, we can just return this. So we can say if not node, or I think it should address that. Thank you very much. Cool. Let's keep going. Oops. Okay, so we are here, and now we have the results and we know the compatibilities. So, which cases we are going to be checking? Now let's remember that again. So, first, let's update our second field before the global result. Because for the global result, we should also check the case where if they are both compatible, right? So now let's go with updating only single line results. If left compatible, and also let's, do we have a result? Let's also create our result. Here int result is equal to make pair 0, 0. If I am compatible with my left child, then I can indeed directly get that result into my second field. And we can say result dot second is equal to left result dot second. So I get one leg from my child, right? And what do I add on top? One, right? Because the edge between me and my compatible child should be added as well. So that's why this is going to be red result dot second plus 1. Does it make sense? So the result is not finalized yet. Like we are still, it's half-baked. We didn't check our right child. But now we get the update from the left child. So if we are compatible with our left child, then we can directly get its result because we didn't consider right result yet. Does that make sense? Okay. So now we are going to check the second part. So now here, let's say, find second field, calculate second field. So if we are also, like if we are right compatible and right result dot second plus 1 is greater than result dot second. So why do I have to do this check for right but not left? And inside I'm going to say result dot second is equal to right result dot second plus 1. Yes, any guesses why do I have to make this check for the right one but I didn't do the same check for the left one? So let's take a look at the initialization of the result. How about now? Any guesses? Yes.
The result from the right tree, subtree, might be less than the result of the subtree, the left subtree.
That's why we need this check right here. And we don't need this. We don't need a similar check here because we initialize it with 0. Like if I have compatibility with left, then I know that left result second plus 1 is gonna be equal to at least 1, and 1 is greater than 0 for sure. So that's why the check here would be unnecessary. But here it's gonna be essential because the left result could have been better, and we don't want to override if that is the case. Cool. So now. We are done with the calculation of the second field, I guess, because since it's coming from one direction, and in the case of compatibility, I can get the result from my children, I think we are respecting all the rules of the question and updating the field accordingly. So now let's calculate the first field. So, in the first field calculation, if I'm not compatible, then I'll directly compare the results from my children, right? So basically there are 3 cases here. I'm not compatible with any of them. Then I'll just get the best global result from both. It will be done. So we can be merging some of the cases moving forward. But first time solving the question, it's better to separate them out. Unless you have too many cases. It means then you are not making a good grouping. But here we have actually 3 ways, right? It's either I am not compatible with any of my children. That's one case that I have to consider. The second case I have to consider is I am compatible with one of my children, either left or right. And the third case I should consider is I am compatible with both children. So now let's see how we would proceed with these 3 different ways. Okay. So here, let's say first case, no compatibility. If this is the case, what we are going to do is, like it means left compatible and not right compatible. What I'm gonna do is, if I'm just gonna get the maximum from both results, right? Result that first will be equal to max. Is there a max function in C++ default?
Yes.
Okay. Max left result that first, right result that first. Because I'm not compatible, I cannot add anything on top of their results. Right? So I have to get the best global result I found so far and return it back to my parent. Does that make sense? Are we clear with this case? Cool. Now let's move on to the next case. Second case. compatibility with both. So this is the case where we need to have the exception of considering, oh, well, maybe we can merge the results. Oh, by the way, I think even for this case, we are gonna need this. So right now I'm gonna take this out. Or let me finish the implementation and then we are gonna do the cleanup, then it's gonna be more clear. So here we say left compatible. If that is the case, we can make it else if, because there is no intersection between these two. If we are compatible with both, like first, the result comes from the maximum of the previous global results. And second, the global result the best result can come from merging two solutions I found from left and right. But not the global solutions, we gotta be careful. Merging single leg solutions, which is coming from the second field, right? So here I will consider a candidate int candidates, or let's say local best, because this includes ourselves, right? This is the best we can do, including our node. So the local best is gonna be, I'm gonna be getting everything on my left. So it's gonna be left result, that's second. All the edges they were found that it's gonna be there. Plus, right result, that's second. Everything that comes from my right? In that subtree, all the edges, they will be included too. Plus, what?
2.
Yes, plus 2. Because I am adding 2 edges, like it's as if I am here. I get one result from here, it is 0. I get one result from here, it is 0. 0 plus 2, because I'm introducing 2 new edges here. Does that make sense? Cool. So, now, you see that first and second cases, they indeed considered this, right? So now let's consider the last case where, oh, actually, my second field is already created. So we can say that if not compatible, it's not going to be getting it from there. Okay, so how about this? If, else if. Oh, because of the comment I don't like this. Third case, compatibility with left. With only left. If this is the case, then first the global result can be this, right? Oh, by the way, we didn't finish implementation of the previous case, because if local best is better than result first, we need to update. Then we are going to say result first is equal to local best. And here we get the best result for result first. And right now, since I am left compatible, I should also say int local best is equal to left result, that's second, plus 1. Does it make sense? Like if I'm only left compatible, the best result that will include myself will be left's result and the edge between us. So this is the case where like you have left compatibility only. So it's something like this. So we have 5 here, 2 here. So this guy, it has only left compatibility, right? So what we are going to do is we are going to get the result from the left subtree, and then we are going to add 1 because of this edge. Does that make sense? Cool. So if we are left compatible, this is what we are going to do. And then finally, we have our fourth case. Initially I said 3 because I was saying, oh, 1 child, but since they are left and right, we are separating into 2 cases right now. And we have fourth case. Fourth case, compatibility with only right, and if actually we don't have to say anything here if we just say else, right? That's the only remaining possibility. And we are gonna say if local best is equal to left result, this time it's gonna be right result. Okay, so now we have local result for this guy, this guy, this guy. And is there anything that you guys are noticing? So the statement result first is equal to max something. It's appearing in all of our cases, right? Meaning we can take this out. And we can remove this case. Both, and we don't need this anymore. And we can even say int local best equal to 0. And then we are gonna do this, and we are gonna remove this update too, because this update will be needed by everybody too. And so we got rid of this line, and now we have a local best defined outside. We got rid of this line. It's gonna be like this. Oops. And this is first, this is second case, and this is third case. And finally, when I hit here, if my local result, local best is better than what's in the result, obviously we have to update, right? If local best is better than, and now we have to update this else too, so it's going to be else if left compatible and right compatible, else if right compatible, else if right compatible and not left compatible. This can be a little optimized, maybe, I'm not sure.
We can do more, not right compatible because if it's compatible with both, it will be handled by the first step. Online 50.
Online 50?
If it's compatible with
Yeah, which one we can remove, you said?
line 55 after the end.
Okay, you're right. So we can remove this, and also we can remove that. Thank you. Yes. And if local best is greater than the result dot first, we are gonna say result dot first is equal to local best. And here, once we reach to here, where are we right now? Oh, it's been plenty of code. Okay, so once we reach here, we can just return our result, right? Return result. All right, so at this point now, let's take a quick look and remember what we have done. So at the beginning, we have initialized the results and compatible with variables. And then we considered our base case. What is our base case for our recursion here? Hitting to the leaf nodes. Once we hit the leaf nodes, we realized from our solution on the whiteboard that we should return 0, 0. And then we first check whether our left child exists. If that exists, then we went ahead and get the result from our left child. And we also checked whether our right child exists. If that is the case, then we also get the result from our right child. So again, Tim, we are approaching in a top-down manner if we are using recursion. And in recursion, after you define the base case, you can assume that all the sub-problem solutions are going to be calculated automatically and they are going to be made available to you. So that's why we are able to do the calls without really making much of implementation up to this point. But then, we also need to calculate the fields, right? There are two fields that we need to report back to our caller. And we started with calculation of the second field because it kind of looked easier to us. Because it was adding ourselves on top of a single line or single direction result coming from our compatible children. And after that, we calculated the first field. So first field is the global result. And for the global result, first condition was check what you have found so far the best from your left and right calls. And then we get this as an initial value. And after that, we checked whether a result that contains us, so by adding ourselves to the results that are coming from our children, can beat the global result that is found so far or not. And if we were able to beat it, we updated it. And as a result, we just returned the result. And that should do it, but we will see. So now is the fun part. So we didn't need this guy, right? Okay. Let's give it a go. No member value.
it should be val.
Val?
Yeah, yeah. just
Oh, there are too many of them. I wish it works like this. Okay, so let's do this manually, guys. Okay, so now let's run another test case.
You can say use the example test if on the bottom. Middle button.
And should I remove the first one? So that it's gonna run the second one?
Uh,
Or is it running all of them? Okay. So are they both two? Alright, so now, okay, in an interview, what do we do? Like once we are done with the implementation, do we say, that's it? No. First we trace it, right? We kind of traced it, like we went over before clicking on the run code. But now we can indeed try to come up with some strong test cases. And indeed we have covered some over here, right? So this 4 case, I think that's a good one. We can give it a try to this one. So how that is gonna look like?
you can use 3 visualizer.
Okay.
Yeah, then,
And how do we add a new node? Oh, it's always a full tree.
no, it doesn't say.
If you open from the end, it will open it to the bottom.
Okay, so now what I want to do is I want to add children to the left 4. So how do I do that?
4, 4.
Where am I going to add?
2 4s at the end. Yeah.
At the end, but I'm not sure if it's going to end to the right place. I mean, this format is not
You can say
No.
null null.
no in before.
Okay, thank you. This makes more sense. Null and 4 4, right? Okay, this makes sense. Okay, so this got accepted. So, like, do we understand why this is a good test case? Because, like, it has the case where it should consider that it's going to be either single. Oh, but actually, they are both giving the same result. So maybe we can improve it a bit. How about this? What if we have one more 4 here? Then the result is going to be 4, right? So it should do the merge here and it shouldn't get 3 from here. It's going to be an even stronger test case. Are you guys able to follow? Okay, cool. So now let's give it a try with this test case as well. And the update we have is just adding one more 4, I guess, right? To the end. Yes, and now the result should turn into 4 now. Yes. And now that like we did tracing and then we tried with different test cases, I think we have enough confidence to click on the submit button. And Tim, again, like when you are having practice, please treat submit button like we are treating it right now. Like as if you're about to hold your girlfriend's hand for the first time or something, okay? Because it's not nice to hit it again and again, because then we are abusing the auto control system and we are not improving our debugging skills. So that's why you can treat it gently. Let's click on the submit button. Success. So this time we got lucky. In some other learning how to approach sessions, this wasn't the case. Like, of course, we are all people. We can make mistakes. That's very normal. But I hope the session was useful to you guys to see how an experienced programmer would approach things. Thank you very much, everyone.
Can we do code cleaning one more time?
Yes, yes, that would be great. Yes. Any suggestions?
Like I think local best can be maximum of the first results. I think
Local best can be.
the result dot first because result dot first is already the maximum that we have checked the compatibility of that.
Local best can be result that first.
Dot second. If it's left compatible, result dot second is left result dot second plus one, right?
Ah, oh, I see your point. So basically what we can do is something like this, right? If it's left, we can just check these two. Local best can start from 0, and we get rid of this, and then we say if it is left compatible, local best plus equal to left result second plus 1, and if it is right compatible, so let's get rid of these guys. And if it is right compatible, we can say locus best plus equal to right result. Because like the merge of these two is exactly what we were assigning in the equality case. Are you guys able to follow this simplification? Like I'll take the code back right now. So look at this. If both left and right, if they exist, our result is left result second, right result second plus 2, right? And we can write 2 as 1 plus 1. And in that case, like if we are left compatible, we are adding left result. If we are right compatible, we are adding right result. And the summation of these two, like left result second plus 1 plus right result second plus 1, it is equal to left result second plus right result second plus 2. So that's why we can indeed make our code a lot simpler by doing this. I'm not sure if you are suggesting this, but maybe even further, or
But I think, should this be else if, or just
if it should be if. If else if, it's not gonna work. Yes. So if we are left compatible, we get the left result contribution, right compatible, get that one too. And if we beat the best result, we update it. How does that look now? Simpler? And that is like SBC, good can always be better, guys. Now let's run the code to see.
plus or plus should it be?
Oh, so these.
Line 14.
Oh, plus equal, yes. It should be like this. Thank you.
We have the same thing.
Ah, okay. Okay. All right. Cool. Any other suggestions for improving code quality? Maybe we can get rid of this guy. I guess the rest is pretty straightforward, so cool.
Oh, wait. If it's right compatible and right dot second plus 1 is greater than right dot second, we can remove the condition and then we can just use the max for the right dot second of of result dot second and right result dot second plus 1.
So which line are you talking about? Sorry, I wasn't.
Line 40,
Line 40, yes.
we can remove the second conditions
Uh-huh.
and we can use the max of the right second plus 1 and the right second if it gets into that condition.
I see. So basically, you're suggesting that we can remove this. If I'm understanding it correctly,
Yeah.
it's going to be like this.
Yeah.
Result that second. Right?
Yeah.
Okay. Yeah, that looks a little better than the other. Yeah, thank you. Any other code improvement suggestions?
If it's not right compatible, right result would be 0, 0, right?
Yes, that's how we initialize things.
Yeah. So if we just write it with max, it will not be evaluating with 0. So we don't have to check if it's right compatible. We just try to maximize.
Oh, right result second. Does the same apply to left compatible? I guess, right?
Yeah.
If it's compatible, it's going to be 0. Oh, but how about plus 1? I think plus 1 may cause a trouble. Because if they are compatible, we can add the plus 1. Because then we can get that edge, right? Yes. Okay. Cool. All right, team. Thank you very much.